All right, let's work through this bell work. Again, a little bit complex here. Don't let the complexity weigh us down, okay? It's going to be a little bit strange. Haley said we are going to subtract 1 and then divide by 2. So we're going to get negative 1/2 cosine of 2x minus 5 pi over 6. So we subtracted 1. We divided by 2. We got to that point. Wonderful. Matthew, what can I do next? Inverse cosine. We want to get rid of cosine, so we are doing inverse cosine on both sides. So we are thinking to ourselves, where on our unit circle is cosine? Is my x value going to be negative 1/2? Which two quadrants would that be true? 2 and 3. We'd be over here. Okay. Well, look at your unit circle. Look at where those are, but it is at 2 pi over 3. And 4 pi over 3. Those are my two answers. Everybody go to that point. Nothing's changed. Just solving like we do everything. What am I going to do next here, Jack, to solve? Add 5 pi over 6 to the other side. In order to do that, we need to get common denominators. So if you want to rewrite it with common denominators first, maybe it's less ugly. So I'm going to rewrite that as 4 pi over 6 and rewrite that as 8 pi over 6. But yeah, we're just getting rid of this 5 pi over 6, so we're adding 5 pi over 6 to both sets of answers. So what that leaves me with is 2x is equal to 4 plus 5. Okay, so 9 pi over 6 and 8 plus 5, which is 13 pi over 6. Everybody go to there. I have an issue here. What is the issue that I just created? I'm not on the interval anymore. At the very beginning, we said that my interval is from 0 to 2 pi. When we added, remember what adding did? Adding shifted my graph. Because it was minus 5 pi over 6, I shifted to the right 5 pi over 6. Are both of these answers between 0 and 2 pi? No. Okay. This answer right here is no longer in between there. Okay. Because think about what 13 pi over 6 is. Oh, that is 2 pi with a 1/6 left over. It's too big. So what means is that 13 pi over 6, that means my point got shifted out of my graph. Well, if a point gets shifted out of my graph, what's going to happen? Another point shifts in. What do you think the new point that shifted into my graph is going to be? It is pi over 6. This one went out. It came back in. We'll see that in a visual here in a second. Okay, but that one went out. You do want to change that now. Okay, if you wait till later, it's going to just throw you off. Just shift it now. That one went out. New one came in. Everybody go to there. Don't forget, this 2 out in front, though, is doing a lot of work. That 2 in front of my x tells me what about my equation? It changes the period length. More specifically, how many times am I going around the circle now? That is how many times around the circle. 2 times around. That's what that means. Pi over 6 and 9 pi over 6 are what I got the first time around. Max, how do I find out the values the second time around? How do I show that the answers the second time? You're going to do that in here in a little bit. What do I need to add to those answers? We're going to add 2 pi. So we're going to take these two answers and we're going to add 2 pi to them because I'm going around the circle again. And since these things have a denominator of 6, that's like adding 12 pi over 6. These two answers were the answers I got the first time around. And then I'm going to add these two answers to find the numbers we got the second time around. So 12 plus 1 is 13 pi over 6. And 12 plus 9 is 21 pi over 6. Now am I done? No, because what else do I still have to do to finish? I got to get rid of this 2. And to get rid of that 2, I got to divide by 2, which is like multiplying by a half. So I get, my answer is pi over 12. 9 pi over 12. Oh, that's 3 pi over 4. This one right here is 13 pi over 12. And then 21 pi over 12. Oh, I could reduce that to be 7 pi over 4. That is a complex question, okay? That is difficult. Don't make it seem like that's going to be what every question looks like. But those are my 4 answers, okay? Again, I think it's really helpful for us to understand what this looks like on a graph. That way it's not just make-believe, okay? But there's an actual reason to how we got that. So let's look at that picture real quick. All right, here were my answers. We did it the first time, 2 cosine, something plus 1. We had 2 pi over 3 and 4 pi over 3. The first thing we did is we shifted this graph 5 pi over 6. So watch those points. We're shifting, boom, boom, boom. They shifted. Oh, yeah, that 13 pi over 6 got kicked out. But when that 13 pi over 6 got kicked out, this new point came in, this pi over 6, which is what we got. Great. Then I've got this b value, the number in front of my x. Oh, it was 1, but as I make it 2, it's going faster and faster and faster and faster. When it goes faster, now I've got more answers. Not only do I have this pi over 12, but 3 pi over 4, 13 pi over 12, and 7 pi over 4. We shifted and then sped it up. That's why I'm getting the answers I'm getting. Questions on what we did there? It's weird. It's not impossible. Okay, don't let it be too difficult for you. Just think it through in the steps we just did. I think it should be pretty straightforward once you do that. Here we go. Number 1, cosine theta over 3 minus pi over 4 equals 1/2. Do it. Okay, you don't need me to help you here. Just try that problem, see what you get. Go. If I want to solve that, Herman, what could you do first? Yep, let's get rid of cosine. So we're going to go inverse cosine on both sides. Inverse cosine, inverse cosine. Okay, so we're getting theta over 3 minus pi over 4 is equal to anywhere that cosine is 1/2. So it's a positive 1/2. So I know I'm going to be on the right side because I'm dealing with cosine. That's not it. That's it right there at pi over 3. And that's right there at 5 pi over 3. Okay, those two things should be pretty straightforward. Once I've done that, Kara, what could I do next? Good. We want to move this pi over 4 over. And in order to add fractions, I got to get common denominators. So that is by far the most annoying thing about this problem is getting common denominators. So I'm going to rewrite this with common denominators first. That way I don't hate myself as much. But I'm going to multiply this on top and bottom by 3. And I would multiply these on top and bottom by 4. But I'm going to get 4 pi over 12 and 20 pi over 12. I got to add that 3 pi over 12 over just like we discussed. It's annoying. I know it's annoying, but you can handle it. So theta over 3 equals 7 pi over 12 and 23 pi over 12. We just added or subtracted. When we add or subtract, we got to think to ourselves, are those answers still on my unit circle? Are they still in my interval from 0 to 2 pi? Yeah, what would this numerator need to be to not be between 0 and 2 pi? 25. 25 or bigger, it's too big. But both of these answers are still in there, so since both of those are still in, nothing new came in. Okay? Nothing went out, so nothing new came in. So those are my new values. If I go to that point, we've got one more thing here. Ooh, I've got this theta over 3. What, again, theta over 3, that's the same thing as like 1/3 theta. What does this 1/3 represent with my equation? That's how many revolutions. I'm doing 1/3 of a revolution, which is weird because so far we've done more revolutions. Now we're doing 1/3. Okay, so think about what that means. 7 pi over 12 and 23 pi over 12. I want to know how many times I hit that if I did 1/3 of a revolution. Tell me now when I've reached 1/3 of a revolution. There, at 100, think about it in degrees. Like there's 360 degrees, 120 degrees. So I got to think, how many times did I get that answer in that interval? Okay, the good news is you don't have to overly think about it because just solve. What would I want to, it's not more than a rotation, so I don't need to add 2 pi. What would I need to do to get rid of 1/3? times 3 times 3 times 3. Boom, that cancels. Theta, 21 pi over 12, and 69 pi over 12. Yeah, there you go. Math's hard. Are any of those not on my unit circle? Yeah, that's way too big. That's too big. This one works, 21 pi over 12. Again, it's less than 24 twelfths, so we're good. The other one's too big. Okay? Understand why. Again, get a visual of what we just did. Okay, so when we graphed this thing, we had this set up. How many times were I equal to 1/12? So pi over 3 and 5 pi over 3. We shifted it. So when we shifted it, we went to the left, 5 pi over 4. Oh, cool. This answer's still in. 23 pi over 12 was still in. And then we multiplied by a third. So that 1/3. Okay, I saw Megan going like this. It's making it wider. Okay, we're taking this thing and it's stretching us out. So this 23, did we do that right? Yeah, 21. Yeah, we did 21 twelfths. I just didn't simplify. 21 twelfths. Oh, yeah, 7 pi over 4. It's still on it. But notice that that other answer that we had definitely got kicked outside. Okay, that one now is all the way over there at 23 fourths. Okay, we could have simplified there and made our lives easier. But yeah, it's out of our circle now. Does that make sense why we did what we did? You just trust the process there. We just solved. If we just solved, it didn't do anything that crazy. All right, let's review Pythagorean identities really quickly. Okay, we know that x squared plus y squared equals 1, right? It equals r squared. Okay, x squared plus y squared equals r squared. That's just Pythagorean theorem. If I wanted this to be in terms of sine, what would I want to divide all of those things by? R squared. Because if I divide by r squared, oh yeah, y squared over r, that's sine. Okay, I'm going to divide everything by r squared. What's x squared divided by r squared going to get me? That is cosine squared plus sine squared equals 1. That is a Pythagorean identity. This is always true. Okay, this is always true. This is never not true. Okay, so we can use that at any time. It's an identity. It always works. And we're going to need them here in a little bit. But just don't forget about that. All right, here we go. We are solving this equation. We are still on the interval from 0 to 2 pi. This looks strange. Don't let it be stranger than it is. 2 sine squared theta minus 3 sine theta plus 1 equals 0. The first thing we want to check for is that everything is in terms of the same trig function. We're all in terms of sine, so we're good. We don't have to do any transformations. So we're good in terms of that. What does this problem look like? Good. Good recognition there. This looks like a quadratic. Okay? I've got sine squared. I've got sine to the first power, and then I've got a constant. Okay? We've done this before, and this is a math trick that's used quite a bit. You could rewrite this so it makes more sense in your brain. Okay? We did this back in probably October. But I'm going to write this as 2u squared. Instead of sine squared, I'm just going to use the letter u. Why do they do that? Not quite sure. It just helps us better visualize what's happening. Minus 3u plus 1 equals 0. Everybody good to that point? Factor and solve. Go. We're just factoring and solving. Don't let it be any harder than that. So whatever makes you happiest to factor and solve, do that. I like borrowing payback, so I'm borrowing that too. So I get this problem right here. I'm sorry, that problem right there. Then I am going to factor. So I need two things that multiply to get me 2 and add to get me -3. So -2 and -1. And then I'm going to pay back. I borrowed that 2 in the beginning, so I'm going to divide by 2 now. So I get u minus 1 and u minus 1/2. Everybody good to there? I factored. Now what do I want to do if I want to solve it? U minus 1 equals 0, and u minus 1/2 equals 0. I'm going to solve it, so u equals 1, u equals 1/2. We just solved, like every other problem we would ever solve. Now what we're going to do is actually solve it with sine. We did it all with u to get to this point, which is great. But we want to know now we're going to resubstitute back in. We started off by taking out sine and making it u. Well, now we're going to take out u and plug back in sine and get to the place where we really wanted to solve, which is answering this thing. I'm substituting back. Now we're just doing the problem. When we answer the question, sine of theta equals 1, where on my unit circle is sine going to be equal to 1? There's only one spot, pi over 2. There's only one place on here where my y is going to be equal to 1, right there at pi over 2. So that is one of my answers, pi over 2. Boom, solved that half. Then I got to solve the other half. I'm doing sine of theta is 1/2. Technically, I'm doing inverse sine, but I'm thinking, where is sine get me 1/2? So when does sine get me 1/2? When does my y 1/2? Boom, right there at pi over 6. And boom, right there at 5 pi over 6. So theta is going to be equal to pi over 6 and 5 pi over 6. All three of those answers work. All three of them are answers to this question. Okay, they're strange. We did it in a weird way, but it's just solving. There's nothing different than solving there. Questions on what we did? We recognized the quadratic. We solved the quadratic. We plugged back in with sine, and we solved it from there. Yes, ma'am. All three of those are answers, yes. If you don't believe me, you could always plug them back in. If you plugged in pi over 2 or pi over 6 or 5 pi over 6, all of them should equal 0 in the end. All right, let's try it again. Going to the backside. Same idea. Again, it looks strange. It's not as strange as it seems. Sine squared plus cosine of theta equals -1. This one we have an issue off the start. Okay, when we look at this problem at the very beginning, I don't like that it has sine squared and a cosine. I don't like that it's in two different terms because we couldn't do that u thing that we just did because one would be u and one would be a different letter because they're not the same thing. So the first thing I want to do is change one of them. I want to change either sine squared or cosine to be the other one, to be sine or cosine. How could I do that? Pythagorean Identities. There's a reason why we wrote that thing on the front of our paper, right? On the front of our paper, we wrote down this. Sine squared theta plus cosine squared theta equals 1. That is a Pythagorean identity. That is a statement that's always true. Who cares if I flipped cosine and sine? They're the same. I want to change this guy. That's the one I'm going to change because it's squared. I'm going to change it, and I want to change it to cosine. So what could I substitute in for sine squared? Yeah, I want to get sine squared by itself. And so I would move this over. So it would be 1 minus cosine squared. That is what sine squared is equal to. Sine squared is equal to 1 minus cosine squared. So for sine squared, I'm plugging in 1 minus cosine squared. I substitute it in. Now I've got everything in terms of either sine or cosine, just one or the other. So we're better now. Now I need to solve this thing. What is this thing as we look at it? It's a quadratic again. Okay? It's an ugly looking quadratic, but it's a quadratic. What is rule number 1 anytime we try to solve a quadratic? Make it equal to 0. Work with your neighbors. See what you can do for a second. So we are trying to make this a quadratic. We're trying to make it equal to 0. So Lydia, what'd you do next? So we moved this over or the other thing over? Did you move this guy or this guy? Added one to both sides. Okay. So we added one to both sides. So I'm just going to rewrite it negative cosine squared theta plus cosine theta. And then she added 1, so it's plus 2. That's all equal to 0. What else should I do here? I don't like the negative in front, right? So what could I do to make it not be negative? Yeah, I might just change all the signs. Cosine squared theta plus cosine, or sorry, minus cosine theta minus 2. I just changed all the signs. Okay. Lydia then said she factored it. If you don't want to write it in terms of u, you don't have to. I would, just because it'll make your brain hurt less. Okay. But as we're doing this, we wrote it in terms of u. So it's u squared minus u minus 2. That's what I'm trying to factor. All we did is change cosine for u, so it made more sense in our brain. Factor that guy. I need two things to multiply together to get me -2 and add to get me -1. So -2 and a +1. I'm going to solve them. So u equals 2 and u equals -1. Questions on how I solved that quadratic? Once we've solved that, then we are going to substitute back in. So I don't really care when u is equal to 2. I want to know when cosine of theta equals 2 and when cosine of theta equals -1. When does cosine of theta equal 2? Never. That is a never thing. That is not going to happen. Cosine cannot be anything bigger than 1 or anything less than -1. So if I get cosines 2, yep, not an answer. Okay, so don't care about that one. When is cosine of theta going to be -1? At pi. Boom, there's my unit circle. That's when my x is -1 out there at pi. So my other answer and my only answer here is pi. That is the only time that statement is going to be true. Again, if you don't believe what we just did, plug pi in. Okay? If I plugged in pi here, it'd be sine of pi squared plus cosine of pi equals -1. Well, sine at pi is 0. Cosine at pi is -1. Oh, yeah, -1 equals -1. That's a true statement. You can always plug back in and check. Okay, but that's the only time it's going to work. Questions there? Let's try one more. Okay, example 3 here. Solve the equation on the interval from 0 to 2 pi. I like it. It's good stuff. No, I'm a big fan. Sorry, we're having a discussion in class. It's very important. Very important. Here we go. Looking at example 3. 4 cosine squared theta equals 1 plus sine theta. What's the first thing we notice here? They're different. I don't like different, so I got to do a substitution. Okay, I want them all to be sine or cosine. So I'm going to substitute. What am I going to substitute in for? The cosine squared or the sine? I got to substitute in for the squared thing because the thing I'm going to use to substitute in is Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. I'm going to take it, substitute, and go. See if you can do it without. Megan, see what you do.
So I substituted 1 minus sine squared theta.
Good. So she subtracted this over, so she got 1 minus sine squared theta. That is what that's equal to. So she is plugging that in. Lovely. Then what'd you do? Okay. Good. Yeah, there's a whole lot of stuff you got to do here. But yeah, distribute that thing. So I get 4 minus sine squared theta equals 1 plus 4. Oh, I'm sorry. I didn't distribute that. 4. Silly goose. There we go. Is equal to 1 plus 4 sine theta. She said, that's a quadratic. I see squareds. I see not squared things. I want to make it all equal to 0. So I'm going to move it over to this side. So this 4 sine squared theta goes over, so now it's going to be positive. That 4 is going to go over, so I'm subtracting 4. So it's 4 sine theta, and then I'm subtracting 4, so it becomes -3. Everybody good to this point? I would then make it u. So 4u squared plus 4u minus 3. I've got a factor. You can factor however it makes you happy. I'm going to do borrow and payback, so I'm going to borrow that 4. I'm then going to factor that thing. So I get u plus 6 and u minus 2, but I borrowed. Don't forget, if you borrow, you got to pay it back. So I borrowed that 4. Now I'm going to divide by 4. So I get u plus 6 fourths equals 0, and u minus 2 fourths gets me 0. So u is negative 3 halves, and u is 1 half. Again, I want to change this back to be in terms of sine and sine here instead of u. So I want to know when sine is negative 3 halves and when sine is 1 half. Questions on something I did to that point? How many of you use borrow and pay back? And everybody else uses their own method? Cool. Or you just don't factor and just act like it's never going to happen? Yeah, it's cool. Factoring's never going to catch on. You don't need to worry about it. All right. So I want to know when sine is negative 3 halves. When is sine going to be negative 3 halves? Never. That's a never. Okay. It's outside of 1 and negative 1. That's too big. So we're never going to be negative 3 halves. When is sine going to get me 1 half? I'm looking at y. I want y to be 1 half. Boom, right there at pi over 6. And boom, right there at 5 pi over 6. Those are the two answers I'm looking for. That's it. Those are the only two places where this thing's going to be true. It's a lot. It looks like a lot. But the math itself is factoring. Can you factor? Cool. Then you can do everything we did today. Oh, you do a little substitutions, and then it's from there. It's pretty straightforward. The trig is pretty light. It's more of just the solving steps that are a little bit tough.